This screencast is going to focus on NMR, which stands for Nuclear Magnetic Resonance. Nuclear magnetic resonance, or commonly abbreviated as NMR, is an extremely powerful tool that essentially gives you information about the entire framework of the carbon atoms. When I use the word carbon framework, that basically means you can map the entire structure. You can tell which carbon atom is linked to which carbon atom, how many hydrogen atoms or a halogen or an OH is linked. So this basically gives you the entire structure, and in that sense it's the most powerful tool. So I'm going to spend some time in giving you the basics of that, so that when we do the lecture, things are much more simpler for you to comprehend. Now, when you think about NMR as a tool, it is an analytical tool just like the IR or the mass spec. Now, there are some similarities, some differences, so let's go over that. First of all, as the word itself suggests, it's nuclear magnetic resonance. That means it's got something to do with the nucleus, right? Comparing that to IR, in case of IR, I was talking about bonds. So I was referring to the changes in the dipole moment, and that means it was more of an electronic property, whereas NMR will be focusing on the nucleus of the atom. So that's one big difference. Another difference would be just the way you run the NMR. The amount of sample that you require for a mass spec is actually very, very little. So on the other hand, for the case of NMR, you probably will need somewhere around like a milligram or so. So it's still a tiny amount. Mass spec is in the tune of like microgram level. So very, very small amounts of the sample still give you the data that you need. So I would still say that as a tool, it's a pretty analytical tool. Pretty good amount of information can be derived from the very modern instruments. And so over the years, of course, NMR as a spectroscopy analytical tool has become a very important technique to decipher the structure of the organic compound. And as we go forward, you will see how and what are the possible techniques within NMR that are available. The closest you can perhaps envision in terms of the health-related field is the MRI, magnetic resonance imaging, which is based on the same principle as NMR. So NMR is sort of, you can say, the mothership for that technique. And just to kind of give you those who are not familiar with MRI, helps you in seeing the soft tissue, and it's a non-invasive technique. And NMR, for that reason, is of course non-destructive as well. So you can retrieve your sample at the end of the day, because it does not break any bonds or volatilize of the material, etc. So realize, in this case, what is used? We use radio frequency, and magnetic field, a combination of that. Now, radio frequency in the electromagnetic spectrum is actually least energetic, so that is why we say that NMR is absolutely non-destructive as a technique. Now, one might ask, what kind of nuclei will give you NMR signal, or is it that any and every nucleus should give you an NMR signal? And the answer to that is those particular isotopes of elements which either have an odd number of protons or odd number of neutrons, they will be NMR active. If you have even number of protons, then those are, or neutrons, then those are NMR silent. That means at any given point of time, at least one or the other, at least the protons or the neutrons, they should have an odd number. And what I mean by that is, let's say you have carbon 12, carbon 13. Okay, now here the proton is 6, neutron is also 6, so both of these numbers are even. So C12, which is the naturally abundant isotope of carbon, that is NMR silent. On the other hand, C13, where the proton is 6 but the neutron is 7, so there we go, you do have odd number of neutrons, and so you would say that C13 nucleus is going to be NMR active. Now the question is, what leads to an NMR phenomenon? And what you need to think about is that essentially when you have a spinning nucleus, so a spinning nucleus is going to basically behave like, or a spinning charge, which is what the nucleus is, it's going to generate a magnetic field of its own. So it's going to behave like a teeny meeny magnet. And so now when you generate a magnetic moment, essentially it's going to, in presence of an external field, it's going to generate two spin states. One is called as an alpha state, the other is called as a beta state. So you can have what we like to say a plus half or a minus half energy states that are associated with it. So one can say that when we don't apply the magnetic field, we have the spins moving in all different directions. So that's like random behavior. Random behavior. And this is in absence of magnetic field. On the other hand, now when you apply the magnetic field, then you are going to align these small tiny magnets in one of the two energy states, or one of the two directions, one which is the alpha spin and the other which is the beta spin. Turns out that the alpha is lower in energy as compared to the beta, and this is in alignment with the magnetic field, whereas beta is in opposite alignment with respect to the external field. So one is in alignment with the external magnetic field, the other is opposite to it. Now, the difference that exists between these two is dependent on the magnetic field. If this magnetic field is pretty strong, then the difference in energy is going to be pretty small as well. And so you have to basically couple this with a radio frequency such that the two states resonate with each other. That means when the external field will be 0, then the two spin states will have the same energy, but as the field increases, then the difference between the two states also is going to increase. So you are looking for that particular magnetic field. You're looking for that particular magnetic field at which the two on application are going to resonate, and that's what we are looking for. To give you a flavor for the kind of magnetic fields that we are talking about, Earth's magnetic field is, about close to about 2.1 Tesla is the maximum that has been measured. But usually on an average it's actually 10 to the power of minus 4 Tesla. But even at the core it's considered 2.1 Tesla, and modern spectrometers, they have such powerful magnets that they can have a field of as high as 21.3 Tesla, so it's like really gigantic. So one reason, or one thing that one must be careful about is when they run the NMR for their sample, you cannot be wearing pacemakers. I don't even want to get into the graphical image as to what would happen if somebody who's wearing a pacemaker gets too close to that kind of a magnetic field. So I still remember from my grad school days we had to always remove expensive watches and cell phones and wallets, and because the magnetic strip on the credit cards would just simply get wiped off at such high magnetic fields. So realize that the magnetic fields are too strong here, but that doesn't necessarily harm the molecule, but more what is magnetically active. So let's talk about what happens when we put samples in the magnetic field. How does that respond? So let's give that a shot. Now, first things first, you can have an NMR spectroscopy of. You can do an NMR spectroscopy of C13. You can do that for proton, but whenever you're running a certain NMR, your spectrometer must be tuned to that specific nucleus to be able to get the radio frequencies which will be sensitive to that particular nucleus. So that's something important, something that needs to be taken care of. But those are parameters that you can set at the instrument, and our job would be to basically figure out what happens essentially when you subject a certain molecule. Where do you get the signal? That will be the next pertinent thing. And why is it that proton nuclei of different compounds will behave differently in an NMR experiment? So analysis of the spectrum is what we are interested in. Now, I said that different compounds will contain different kind of nuclei, and they are going to behave differently in an NMR experiment. And the question is why? And the answer to this question basically lies in the fact that electrons surround protons. Let's say, so the most popular spectroscopy is the proton, followed by the C13. That's the second most important one. So if you have electrons surrounding the protons, in case of the covalent compounds, since electrons are charged, right, they're going to move in response to the magnetic field. That's one thing. And this would generate a secondary field which is going to be opposite of the magnetic field that has been applied. So you can consider that this is kind of like a blanket that is shielding your proton from the magnetic field that has been applied. So you can consider that you have your little nucleus which is positively charged, and you have the electronic environment around it, and you have a magnetic field, okay, that is associated. So if this electronic cloud, if this is thick, essentially the extent that the electronic cloud shields this inner nucleus is going to be to a greater extent than otherwise. And so realize that the amount of magnetic field felt by this nucleus depends upon the kind of electronic environment that it has surrounding it, which is why if you have compounds such as, let's say, CH4, in which you have carbon and hydrogen, and there's nothing that's really electronegative in this case, and you compare that to perhaps something like HCl, in which chlorine is more electronegative, so that pulls the electron density away from that proton. So if you compare the proton in HCl to a proton in CH4, they are going to show up at different locations. And the reason for that is because in case of CH4, the hydrogens are not connected to anything electronegative. The electronic environment is still shielding this proton from that applied magnetic field, and so we say that these kind of protons are shielded, or they are upfield. That means in order to be able to see them, you will require a greater amount of magnetic field. On the other hand, in case of HCl, since chlorine already pulled the electron density towards itself, now that particular proton is pretty nascent, it's naked, and so you don't require as much magnetic field to be able to view it, or you can say that this is de-shielded. And the word for that is down field. When I was a student, I used to just remember the D and the D for the D shield and the down field, and that has always worked for me. So, more electronegative elements, that basically means it's a D-shielded environment. More or less electronegative elements, that basically means it's a shielded environment. Let's see what will be the result of this. Now, all NMR numbers or NMR values are reported on what is called as the chemical shift or delta scale. Chemical shift or delta. It varies between 0 and 10 for the most part. So this is the same as IR, in which our sample basically showed wave numbers, lambda bar, and it varied from 400 to 4000. This is going to vary between 0 to 10. Now, so each time when you have to refer to a value as to where it's showing up, you refer to it as a delta. More a signal is on the right hand side, you will call it the upfield or the shielded zone. More it is on the right hand side, you will call it the downfield or the de-shielded zone. So just to kind of give you a flavor, let's say you want to compare CH3Cl to CH2Cl2 to CHCl3, and I tell you 1, 2, 3, 4, 5, 6, 7, and then 8, 9. Okay, there were only 2 remaining. Okay, so, and I tell you that CH3Cl, that shows up around 2.8, suppose. Okay, so you get one peak at 2.8 for CH3Cl, and I ask you to predict the CH2Cl2. Where would you predict the peak be? More on the left side or more on the right hand side? So you should be thinking right now that, well, chlorine is electronegative, and if you have an electronegative group which is going to pull electrons towards itself, these protons are going to be pretty naked, pretty nascent. They're going to be seen easily by the external magnetic field, and so your CH2Cl2 should be a little bit more de-shielded in that zone. And likewise, because for the same reason, if you consider CHCl3, that should go further on. So realize that more is the number of carbon atoms, chlorine atoms on that carbon. Essentially, the effect is going to be greater. So if somebody now asks you CCl4, where would that be? What should your answer be? I'll give you 2 seconds to come up with an answer. Yes, CCl4 is not going to show up on this proton NMR, because realize we want to see a proton. So if that does not contain a proton, we don't have to worry about it. So CCl4 will not show up on this proton NMR spectrum. All right, let's take a look at essentially where do these signals come in, and how do we decide what is an unambiguous way to make sure that the numbers that we are seeing are or have been auto-zeroed. Okay, so let's take a look at that. Now, one method to do this, to report the location of an NMR signal in a spectrum relative to a reference signal, and the reference signal that we use is usually tetramethylsilane. And tetramethylsilane, the structure of that is CH3,4Si, and that basically is considered it is considered pretty unreactive. The other advantage for that is that It gives a very nice single sharp signal which does not interfere with the resonances observed for organic compounds. And because the hydrogens are connected to carbon, which is connected to a more electropositive element, that is what is randomly selected to be at 0. If that would be connected to something like nitrogen or oxygen, then it would be in the same region as where you expect your signal to be. So you would be missing on, if you auto zero that, then you would be missing on a lot of signal. So that is why they chose something which is more electropositive, and of course it's volatile as well. So after you're done, you can just evaporate it and get rid of that TMS. So that is the internal standard that we use. Now, just like the IR, you will be given a proton chemical shift range table. So you're not supposed to memorize numbers, but just kind of have a general feel qualitatively as to which region should be for which kind of compound. So you can predict things, pretty quickly for yourself, and you don't spend too much time just in going through that prediction. But I want to go over some examples just to kind of see where you guys are at. For example, and we are going to, of course, spend the time through the PowerPoint as well. But let's say I had an ester. Okay, so I have CH3 over here. I have 3 CH3s over here. And somebody asks you, what do you predict in the NMR of this particular compound? Well, realize that an NMR is going to show you the kind of electronic environments that are present, the kind of chemical environments that are present. If those chemical environments are different, they are going to show up as a signal. What does that mean? That means that the methyl that you have here, which is connected to the oxygen, is going to be a different kind of methyl than the one that is connected to this carbon. So the methyl A is different than the rest of them. And notice I called all 3 of them B, and the reason for that is because those are all connected to one single carbon, which is connected to C double bond O. So it's a symmetric situation. What does that tell you? Now, that tells you that this particular compound should give you 2 peaks, and it's going to be between 0 to 10. And now if it's time to think about, let's say, which one is going to be more downfielded, realize that this methyl is directly connected to an oxygen, which is an electronegative element. On the other hand, you have the 3 methyls which are connected to a carbon, which is connected to a carbon, and that is then connected to oxygen. So it's far away from the electronegative elements. What does that mean? That means that you will have 1 peak in the saturated alkane region. You're going to have 1 peak which is going to be more deshielded, and that's reflective of the B protons. This is reflective of the A protons, and you can figure out, you can determine the area under the peak, and that area under the peak will give you area under the peak. That will give you the number of such protons that are present. That means if you figure out the area of the A peak, that should come out to be approximately 3 protons, and the one under the B proton should come out to be about 9 protons. What's pertinent here is that the numbers that you will get may not exactly be 3 and 9. They might be reflective of 1 to 3. Or they might be reflective of 2 to 6. So it's a relative ratio that it looks for. It's not an absolute ratio. And since it's a fraction, it doesn't have to be exactly 3.00. You could see a 3.1 or 9.2. And so you just go for the nearest whole number to look for that particular proton. Okay? Likewise, if you consider perhaps let's say your structure is this. Okay, this is paraxylene. Paraxylene. xylene. And somebody asks you, how many peaks do you anticipate? Well, realize there's a symmetry thing going through this molecule. So looking at that, you can say that the hydrogens here are exactly same as the hydrogens over here. So there will be one peak corresponding to the hydrogens on the ring, and then you have a methyl and a methyl here. So there'll be one peak corresponding to the methyl group. So if you try to predict that, 5, 4, 3, 2, 1, 6, 7, 8, and 9. So aromatic peaks, they show up at about 7. So there'll be one peak corresponding to 4 protons, and there will be one peak at around 2, because that's the benzylic position, which will correspond to 6 protons. So they are going to be in the ratio 3:2. And that's what you will expect. Now, let's go over one or two more before we proceed further. Let's say this is your molecule. So you have T-butyl group and an aldehyde. Notice you have a lone soldier aldehyde, which usually shows up around 9.1 delta. All the 3 T-butyls, that's the second group, so you again expect only 2 peaks. One peak for the alkyl region at around 1, and one peak corresponding to only 1 proton at around 9. And that's all that you will see. Okay, so you can we basically went over 2 things. One, you can look at the number of chemical environments in the molecule, and corresponding to that, you will have the same number of peaks on your NMR spectrum. And if you integrate the area under that peak, essentially that will give you the number of such protons. So for example, in this case, they are going to be in the ratio 1:9. Now, what's the last part of an NMR? What else does it tell us? Okay, so the spin-spin interactions. Spin interactions, sometimes also referred to as the spin-spin coupling. Spin-spin coupling. What does that mean? Now, I'll give you 2 examples. Let's say we have 1,2-dichloroethane. 1,2-dichloroethane. Okay. And I have 1,1-dichloroethane. So there is 1 hydrogen here and a CH3 here. Hopefully you can see 1,1-dichloroethane. Hopefully you can see that in case of 1,2-dichloromethane, there is a mirror plane which basically divides these 2 into 2 equal halves. So all you expect in this particular spectra is 1 peak. Possibly around, my guess is 3.5 delta or so, because there's chlorine close to it, so it's going to be a little bit deshielded, and you're going to end up with just 1 peak. On the other hand, if you think about the spectra for the case of 1,1, you should see 2 environments, one which is going to be more upfield, the other which is going to be more downfield, because it's very close to 2 chlorines now. Turns out that your spectra is not just simplified, that you have 1 peak at 1 and another peak at, let's say, 6. The peak that actually shows up at 6 is a mixture of, it's a combination of 4 peaks. So it shows up as a quartet. And the peak that you get at 1 is not really just a single peak, but rather a combination of 2 peaks, which we like to call doublet. The question is, why would this happen? Turns out that whenever you have hydrogens which are very close, they're in close vicinity to each other, realize all of these are spinning, and each spinning charge is basically a tiny magnet. So each magnet is going to see other magnets in close vicinity and obviously interact with it, and so it's going to split those that are pretty close to it in two or more resonances, depending on the number of neighbors that it has. The rule of the thumb here is that if you have identical environments, such as what you saw in case of 1,2-dichloroethane, it was exactly the same environment, they're not going to split each other. And the reason for that is because their splittings are going to overlap. They are going to fall right on top of each other. So these are considered that they are non-splitting in nature. On the other hand, if you do have a situation like the 1,1-dichloroethane, you're going to follow the N+1 rule for splitting. What that means is that you are going to count the number of neighboring protons, add 1 to that, and that will be equal to the number of splits for that particular peak. What do I mean by that? Let's consider the A protons and let's consider the B protons. And what I said was that the peak at 1, which is the A proton, is a combination of 2 peaks, and the peak at 6, which is the B protons, is a combination of 4. How did we get those numbers? Well, if you're looking at the A protons, how many neighbors does it have? It has only one neighbor. So this one neighbor has the potential of splitting the 3 hydrogens. 1 plus 1 times implies 2 times. So this particular peak, which is reflective of the methyl, is going to be split twice. On the other hand, when you look at the B protons, which is just 1 proton, since it has 3 neighbors, 3 plus 1 is 4, which is why it's split as a quartet. So if you just see one single peak, we use the word singlet. If you see 2, you call it a doublet. If you see 3, you call it a triplet. Quartet. For 5, we use the word quintet. Septet for 7. And if you can't count, if it's too much, you just use the word multiplet for many. Okay. And depending on the separation of these peaks, one can actually make a call. That separation is called as coupling constant, or J coupling. You don't have to worry about that as much. Grad school, you'll learn more, or if you are a chem major, junior year or senior year, you would learn more about that then. But right now, just realize that nuclei that have same chemical shift or the exact same chemical environment, they are not going to exhibit spin-spin splitting. The splitting occurs with only close vicinity hydrogens. That means usually neighboring hydrogen atoms. So that means you're not going to see something that's 5 carbons away. You're not going to see splitting in that case. And in terms of splitting, if you have to predict whether it's a doublet or a triplet or what, then you just follow the N+1 rule. In order to get there, you basically say that you look at the number of neighboring carbons and you predict whether a singlet or a quartet or a triplet, what will be generated. So for instance, if you had something like, let's say, a carbon, and there's a hydrogen over here. This hydrogen, look at the neighbors. This hydrogen is on the first carbon. Look at the neighbor. Does he have any carbons? No. That means this is going to show up as a singlet only. Make sense? If you see, on the other hand, you have a hydrogen here and a hydrogen here, and this goes to carbon, this goes to carbon, this goes to carbon as well, and then there's oxygens or whatever. Now this has one neighbor, this has one neighbor as well. So these two are going to split each other as a doublet. That's right. Turns out if their environments are exactly the same, then they are going to overlap. That doublet is going to overlap, so it will amount to two hydrogens. That's a different story. But realize that they do split each other because each of them is a tiny magnet and is going to see, or is going to view each other as another tiny magnet, so it's going to interact or try and interact with it. Likewise, if you have three, that would be a triplet. If you have four, you have a quartet, so on and so forth. You can predict these on the basis of what is called as Pascal's triangle. Pascal's triangle, where one peak can be split into two, so their intensities are going to be exactly the same. If this was a triplet, 1 plus 1 is 2, and you write 1 again, so a triplet is going to be such that the middle one, it has double the intensity of the side ones. Doublet means both of them should be equal intensity. Singlet means only one peak. If it's a quartet, you would say first peak as is, 1 plus 2 is 3, 2 plus 1 is 3, and this is 1. So the first peak is small, second peak is 3 times that size, third peak is 3 times that size, fourth peak is 1. So intensity of 1 and the last one is going to be exactly the same, and the two middle ones is going to be 3 times the ones on the side. Likewise, the next one, 1, 4, 6, 4, 1, so that will be a quintet. 1, 5, 10, 10, 5, 1, and you can build it further on. That's what the Pascal's triangle is, and it basically gives you information about the intensity of the small peaks within that doublet or triplet or quartet, as the case may be. So that is NMR spectroscopy in about 30 minutes. Carbon NMR is it follows exactly the same story as NMR, where every carbon signal is going to give you the number of such carbon atoms. So concept-wise, it's the same thing, and like I said, we are going to focus more on the proton NMR, but I just want to give you a flavor for some questions, like if, for instance, in this case, the molecular formula is given and some information about NMR is given, and you have to come up with what are the possible structures. So you're given that only 2 peaks are obtained, one at about 1, the other at about 3. The first and foremost thing you should do is try to figure out the degree of unsaturation. And so the number of carbon atoms minus half the number of hydrogen atoms. You don't count oxygen. Nitrogen is not present here, so we're just going to say plus 1. So that means 5 minus 6 plus 1, which is going to be 6 minus 6. And so there is no degree of unsaturation. That tells you no double bonds, no double bonds, no double bonds, no rings, no rings. So now you have to arrange the 5 carbon atoms in such a manner that it's reflective of only 2 peaks, and both of these peaks are about the same intensity, and you have to come up with a structure. How would you go about it? Now, you might start thinking about, things like, okay, I have 2 oxygens, how could those be present? Maybe it's a possibility that it's an alcohol. And so let's try to put some structures out there. Realize that if it were an alcohol, then that OH is going to count. So that will be one environment. This will be one environment, which will be same as that. And these 2 will be one environment, and that will be one environment. So that's 4 environments. You need only 2. So this is not your possible option. Another thing that you should think about is that if it's an alcohol, that usually shows up as a broad peak on your NMR, and I don't see any broad peak over here. Plus, the intensity is pretty similar for both of these. That means the number of hydrogen atoms that are present in each of these, in each of these peaks, um, that's approximately same. So since there are only two chemical environments, we have to start placing them, and one of them is more deshielded. It could be next to another electronegative element, and the functionality there that I'm thinking about is an ether, because in your head you should be thinking, well, I know carbonyl, but carbonyl will be a double bond, and I'm not supposed to have a double bond, so it cannot be a carbonyl, it cannot be a carboxylic acid, it cannot be an ester, it cannot be any of those, it cannot be OH because there's no broad peak. So what remains? It's an ether that remains. So how about I place an ether, an OCH3, right? And since I have two of OCH3s, I'm going to place them like this. And I'm going to try to connect this to something. So my oxygens are taken, 6 out of my 12 hydrogens are taken. What if I connect it to a carbon, but realize I'm supposed to make it symmetrical? Now my other peak is supposed to be at 1, so it should not be connected to anything electronegative. And notice the way I have the two methyls here, they are not connected to anything electronegative, and so that gives you information that these are your possible structures, or one of your possible structures can be the one that I have, for the reasons that we just described above. So the number of chemical environments, that tells you these two are going to come together for the A peak, these two are going to come together for the B peak, and that is what you're going to see with no splitting pattern. That is what you're going to see as your overall structure. Let's take a look at the same molecular formula but a different NMR. So in this case you have a triplet, in this case you have a quartet, and in this case you have a singlet, and so there are 3 different chemical environments. So again, it's just the same way as we started. Get the DOU, and in this case it's going to be 12 divided by 2 plus 1. That comes out to be 0. So again, you don't have any OHs, any C double bond O, because no broad peaks, no degree of unsaturation. So the question is, if it's an ether again, how can we arrange those? So a couple things here. If this is a triplet, what does that tell you? That should tell you that it should be connected to, so this is a triplet, that means it will be connected to 2 hydrogens. That means it is going to be connected to 2 hydrogens, and if it's a quartet, then it's going to be connected to 3 similar hydrogens, and of course if it's a singlet, then that's connected to no hydrogens. So let's start there. Now in this case you're not given any information, but if information was given about the nature or the kind of or the number of such protons, of course life will become a lot easier. But the fact that here you have one which is not connected to any neighboring hydrogens, I'm going to put that as a CH2, which is connected to perhaps 2 oxygen atoms, because carbon is supposed to make 4 bonds, and right now I'm putting it as a CH2, and that is reflective of the fact that this particular these particular hydrogens, they are going to show up all the way very deshielded, and they are connected to no other hydrogen atom. So that makes sense. Now that should be connected to, notice the number is pretty deshielded as well, so connecting to 1 oxygen makes sense. And what if that is a CH2 and a CH3? So that would tell you that these 3 protons are going to split the CH2 like a quartet, and the 2 protons are going to split the 3 hydrogens like a triplet. So you can say anytime you see a combination of a triplet and a quartet, you can envision that there might be an ethyl group going on within the structure. And in this case, that ethyl will have to repeat itself in order to account for the number of carbon atoms and the number of hydrogen atoms. I think I'm going to stop here, and this amount of information is going to kind of set the stage, and of course we are going to discuss this in good detail and practice more in class.